Welcome to our fourth and final unit of this first semester. In this unit, what we're going to do is we're going to be applying the derivatives we learned over the past unit, and we'll be doing lots of different things with them. The first thing that we're going to be talking about are related rates. What a related rate is two or more variables that are changing at the same time and what you want to do is you want to find the rate of change of one variable based upon the rate, or potentially rates, sometimes more than one thing is moving, of change of other variables. With related rates, there are some very common questions that kind of show up over and over. And I remember learning this back in when I took calculus and found it to be very difficult. But as we go more and more, I find it not to be quite as bad. So the next little bit is just going to be a bunch of different examples of related rates. There's not really any new derivatives or anything like that to take. But what you want to do with related rates is you want to make sure that you write down and identify all the information that you're given, and then also identify what they're asking in the question. Make sure you read the question very carefully. Oftentimes that we differentiate with related rates implicitly over time. So things are changing over time, like a car is moving away from an intersection, or you're blowing up air into a balloon, so the radius is changing and the volume of the balloon is changing. Let's just take a nonsense equation first. Let's say we have the equation 3x squared plus 2y minus 5 is equal to 0. And the question would be to find dy dt, find the rate of change of the y variable over the rate of change of time when x is 4 and dx dt, or the rate of change of the x variable over time, is equal to -1. So what you're going to do is you're going to implicitly differentiate this equation over time based on this third variable. So when I take the derivative of 3x squared, I'm going to get 6x, and then I have to multiply that by the rate of change of x over time, rate of change of time. So times dx dt plus 2 times dy dt. And one of the things, again, you have to multiply by dy dt because you're taking the derivative of y, so you're differentiating over time on each one of these. And one of the common mistakes I see is that when you take the derivative of the minus 5, that's just 0. Sometimes people leave the minus 5 in it, and it becomes a big problem. And then from there, once we have that, it's equal to 0, we can go ahead and substitute in. For x, I'm going to put in 4. For dy dt, I put in -1. For dx dt, I put in -1. And then we just solve for dy dt. So I get 6 times 4 times -1 plus 2 times my variable dy over dt equals 0. And I solve that, and I find dy dt is equal to 12. Oftentimes in these problems, you're going to be finding different rates of change, like a radius, or it'd be in miles per hour and feet per second, inches per minute, something like that. But in this particular kind of nonsense example, this first example, there are no units of measure. In our second example, let's take a look at the rate of change of an area of a circle based upon the rate of change of the radius of the circle. So remember that, and for our AP exam and for our testing quiz and stuff like that, if you need any of these geometry formulas, they give it to you. Area of a circle is pi r squared. I expect you would know that one. And let's say that we're putting air into the or excuse me, let's say that we have the rate of change of the radius of the circle. Let's say we're pouring like pancake batter onto a skillet or something like that, and the radius is changing at 1 centimeter per second. So the change of the radius, so dr over dt, is equal to 1 centimeter per second. And what I want to find is what is the rate of change of the area of the circle. So I want to find dA over dt. That's my question mark. I always want to identify that. And let's say we want to find the rate of change of the area of the circle exactly at the instant when the radius is equal to 3 centimeters. So I'm looking at the rate of change of the area based on the rate of change of the radius at a particular snapshot. Differentiate the area formula, so dA over dt is equal to 2 pi r times dr over dt. Again, differentiating over time, okay? dA over dt, this is the variable I'm trying to find. I know what r is. I can put 3 in here for r. I know what dr over dt is. I can put 1 in there for dr over dt. So dA over dt is going to be 2 pi times 3 times 1. Multiply that out, what I'm going to find is that dA over dt, the change of the rate of change of the area of the circle in this particular scenario, is going to be 6 pi. And again, remember, we're looking at units of measure, so it's the rate of change of an area, so it's got to be centimeters squared per second. And centimeters squared per second. What happens here is the radius is in centimeters, and the rate of change of the radius is also in centimeters, or centimeters per second. So centimeters times centimeters per second gives us a centimeter squared per second. In my next example, what I'm going to do is I'm going to take a look at the volume of, say, like a volume of a balloon. And this time what I'm going to tell you is that, well, first of all, the volume of a sphere, and we're going to pretend like my balloon's a perfectly good sphere, which is 4/3 pi r cubed. And let's say that I'm going to tell you that the change in the volume, I'm putting air in this balloon, so that the change in the volume is going to be 3 inches cubed per second. That's a cubed, not very good. That's cubed per second. And then let's say that I want to find the rate of change of the radius exactly when the radius is 5 inches. So what I'm going to do is I'm going to differentiate, and when I differentiate over time, on the left-hand side, dV over dt is equal to, when I take the derivative of this side, I get 4 pi r squared times dr over dt. dr over dt is our variable in this particular scenario. Plug in the values that I know. For dV over dt, I have a 3. That equals 4 pi. For r, I know that's 5. And then I'm going to square it, and that's times dr over dt. Just be very careful. I know that sometimes in the problems I give you, or sometimes of the stuff we have, the units of measure will change. Like certain things will be in inches and other things will be in feet. Just be careful about that. If I multiply this out, this is 100 pi. So dr over dt is going to be 3 divided by 100 pi. And if I look at units of measure, it's the change of rate of the radius, which is going to be in inches per second. Not in inches squared, but inches per second. It's a radius. It's a linear measure. There's also some very common examples using Pythagorean theorem, and they don't give you Pythagorean theorem. They won't give you that on the AP exam, and I won't give it to you on my tests and quizzes. I expect you to know it. So remember, c squared, the hypotenuse, is equal to a squared plus b squared, the two legs. Those are arbitrary values. And let's say, sometimes one of the things that get people most confused about Pythagorean theorem problems is sometimes that you have all three distances changing, and sometimes you only have two of the three distances changing. What I'm going to do is I'm going to start out with an example here where we have a ladder leaning up against a house. So let's say we have a 17-foot ladder. I'm going to draw a picture of it. That's my house. This is the ground, and here's my ladder leaning on the house. And let's say that my ladder is 17 feet, and I'm up on the ladder and I'm trying to put something on my house, and the ladder unfortunately starts to slide, and as it slides the bottom of the ladder goes away from the house and the top of the ladder comes down the house. And I got to give you a little bit more information. So let's say that I tell you that I want to find the rate of change in which the ladder is going down the house exactly when the ladder is 8 feet from the house, if the base of the ladder is moving away from the house at 2 feet per second. Wow, that's a lot of information. So let's define our variables. First of all, obviously our hypotenuse is C. Let's allow this bottom side to be A. Okay, and we know something about that. That means the rate of change at which A is changing is dA over dt. Let's let this left side be B. And rate of change at this is dB dt. In the scenario that I made up just a moment ago, I want to know how fast the ladder is going down the house, so I want to find that dB dt. What I told you about A is that I wanted to find the rate of change in which the ladder is going down the house, specifically when A, or this bottom, when it's 8 feet from the house, so this is 8 feet, if this base is moving away from the house at 2 feet per second. Okay. So I have all my information, close to all my information. One of the things I need still is I need the B value, and by Pythagorean theorem I can find B to be 15 feet. And now I can differentiate this. So I get 2C times dC dt equals 2B times dB dt plus 2A, running out of room, times dA dt. And in this particular problem, the hypotenuse is not changing because the ladder is not changing size. It's 17. So this part to the left of the equal sign, that's just going to become 0. I know all the other variables. For B, I'm going to put in 15, so 2 times 15 times my variable, dB dt, plus 2 times 8 times 2. Sorry, I'm squeezing that in there. And I solve that, and I find that dB dt is equal to negative 16 over 15, and that's feet per second. That's how fast the ladder is moving down the house. And the reason why this is negative is because the distance from the top of the ladder down to the bottom or down to the ground is getting shorter and shorter and shorter. It's getting smaller as opposed to larger. If you're a car and you're pulling away from an intersection, it's getting larger, but if you're a ladder falling down a house, it's going to get smaller and smaller and smaller. There are tons of examples of related rates out online. Check some of the websites if you're having some trouble. Check some of the websites I've also shown you. The ones I give you today for the first part of homework, it kind of falls into these categories. And there's just different scenarios. There's no true cut way of doing it every time. You just got to kind of write down everything you know, figure out what they're asking you, look at the relationship between the variables, set up your equations, and go ahead and solve them. So good luck on related rates. You can take a couple days to struggle around with it and see what you can do, get some help in class, and whatever clarification you may need.